Hello everyone, my name is Zhijian Yang. Today, I'm going to present AR, Indoor Acoustic Augmented Reality on Earphones. We know that human brain has the ability to infer sound geometry. When a sound source is at angle alpha relative to the human ears, it actually creates a time delay delta t alpha at 2 ears. By analyzing this time difference of arrival at 2 ears, human can tell in which direction the sound is coming from, and we call this kind of brain ability the binaural ability. This means by artificially injecting delays in the two earphones, it is actually possible to make the brain believe that the sound is coming from a desired direction, and we call such artificially created sound binaural sound. Of course, as the user turns her head, the earphone will turn and the sound will also turn along with it. But if we want to fix the global location of the sound, actually we can do it. We just need to track the orientation of the head and create a binaural sound by compensating for the head rotation, and this is made possible by smart earphones today which have an IMU inside. So leverage this binaural sound from earphones, we can enable a lot of new applications, and this paper focused on one of these applications, acoustic augmented reality. Let's imagine that you are in an airport rushing towards your gate. AR would offer great value in navigating you to your gate quick and elegant. AR can serve as a virtual person walking in front of you, and you just need to find the virtual follow me sound from the earphone, and you can reach your destination. To build such a system, the key research question is to design the binaural sound in the earphone so that it appears to arrive from the right relative location with respect to the earphone user. So essentially, if the binaural audio says, "Should your check-in here," then the audio should indeed come from the place where the check-in counter is, no matter where the user is or in which direction the user is looking at. And the key research question can be further divided into 3 sub-questions. First, user's indoor location. Second, user's head orientation. And third, how can we generate the real-time 3D binaural sound for the user? Let's look at them one by one. First, localization. We use IMU for localization here because this does not require any infrastructure and can make our AR system deployable at any environment. And of course, IMU localization has been studied for many years in our research community. However, most past works rely on IMU that is located on the lower part of the body. For example, smartphone or smartwatch. And now we have the smart earphone IMU, which is on the upper part of the body. Can we leverage this IMU in smart earphones to achieve better localization? It turns out, if we plot the air IMU and phone IMU signal and compare them, the air IMU shows a much cleaner sinusoid signal. This is essentially because human skeleton is a low-pass filter, filtering out all the random motions and make the signal much cleaner. By leveraging this clean IMU signal on the air, we build our dual IMU-based localization algorithm. So the algorithm takes input from air IMU, phone IMU, as well as human motion model, and the output is better localization. And we prove that the fusion of dual IMU is effective in making localization much more accurate. And of course, we also use air IMU for gaining direction tracking so that we can make the binaural audio independent of user head orientation or user location. And finally, we render the binaural audio in real time based on user's location and head orientation, and we also identify humans' ability to perceive binaural sound is an opportunity for localization error correction. I'm unable to cover the details here, but for more information, please refer to our paper. We implemented our AR system on off-the-shelf hardware and evaluated it in our building lobby. We placed a number of audio annotations in the lobby and asked users to retrieve them. The results are promising. Of course, this is just a very quick overview, and for more details, please refer to our paper. Thanks for listening.